Now question 3 is to do with intermolecular forces and basically giving you examples and asking you to explain certain properties as it relates to nitrogen triiodide, nitrogen trichloride and nitrogen trifluoride. Now in the information that we've got the electronegativities, and obviously that's going to help us with having some understanding of the permanent dipoles, for instance, and just looking at that. Nitrogen is obviously common to all of them, and it's immediately apparent that chlorine and nitrogen have a fairly similar electronegativity, so we wouldn't expect a significantly permanent dipole there. Nitrogen as compared to fluorine, they're reasonably different in terms of electronegativity, so I would expect some kind of permanent dipole or a dipole between those two atoms, and obviously the actual molecular symmetry would determine whether we had an overall polarity for the molecule and whether those dipoles cancelled or not. And if we look at iodide, then iodine, again we get a reasonably different electronegativity, but not quite as much as between nitrogen and fluorine. Okay, now when we consider bonding with molecules, all molecules are going to have temporary dipole bonding, and that really just relates to the molar mass, and the bigger the molar mass, the more electrons and the more significant the temporary dipole is. Some molecules will have permanent dipoles, and the greater the difference in electronegativity, the greater the dipole there is, although we have to consider the actual shape of the molecule to determine whether it's going to be polar overall, and whether these dipoles cancel. And then the strongest of all, we've got hydrogen bonding. And when we look at the overall strength of the bonding in a molecule, we need to look at all three. If a molecule has a permanent dipole, that means not only does it have this permanent dipole, but it also has temporary dipole bonding, as all molecules will have that. And one of the things you have to realize in answering scholarship questions, if for instance a molecule has only temporary dipole bonding, but it obviously has a higher boiling point or melting point than a molecule with permanent dipole bonding, even though we're used to thinking in terms of more permanent dipole bonding is going to be a stronger bond, which it is, obviously in the molecule that has temporary dipole bonding, if it's stronger, it usually means it's going to have a greater molar mass, and that will usually give us the information that it's going to be the strongest bond simply due to the fact that it is bigger, there is going to be more electrons present, and it is going to end up with a stronger bond. So we look at the information we're given and we evaluate which one of these three things is responsible for the strength of the intermolecular bond. Okay. Now when we consider these three molecules, they're all going to have a similar shape in terms of they've got three atoms bonded to the central atom, which is nitrogen, and nitrogen has a lone pair. And obviously that means if we've got three bonding and one non-bonding, that's a trigonal pyramid shape, and that the dipoles that may be caused by the nitrogen to the iodine are going to end up not cancelling out because it's not a symmetrical molecule, and therefore it's going to be polar. That's essentially true for the other two, but of course when we consider nitrogen and chlorine, for example, these are so close in terms of electronegativity that they wouldn't create much of a significant dipole anyway. So let's look at that information now. If we have nitrogen to chlorine, which is 3.16, that's very close. Nitrogen to iodine, which is 2.66, that creates a slight permanent dipole. And then if we consider nitrogen to fluorine, which is 3.98, that's 0.94 difference. That would create the most significant permanent dipole. Okay, now we look at nitrogen with iodine. It's going to have a slight permanent dipole, as we said, but also when we look at it and considering the temporary dipole bonding that could go on, we're looking at the size of the molecule itself. Now with 3 iodines present, and iodine being the largest atom out of iodine, chlorine and fluorine, that means this is going to have the greatest temporary dipole bonding. So not only does it have a slight permanent dipole, it's also got the possibility of having the greatest temporary dipole bonding. Nitrogen with chlorine has a very slight permanent dipole, but it's going to have greater temporary dipole bonding than fluorine simply because it's got a bigger molar mass. So when we look at the differences between those two, Ni3 is a solid, so we can explain that in terms of the temporary dipole bonding and the slight permanent dipole, creating the most significant attraction between them, meaning it's going to be those bonds will take a lot more energy to break compared to the other two, and it's more likely to be a solid. If we look at nitrogen and chlorine, the fact that it's only got a very slight permanent dipole tells us that the most significant bonding present must be the temporary dipole bonding. So the reason that this is a liquid and fluorine is a gas in the trihalogen compound means that for the nitrogen chlorine, that's the most significant bonding, the temporary dipole bonding. And in nitrogen fluorine, obviously permanent dipole bonding with a small amount of temporary dipole bonding compared to the other three. So in answering this, you'd need to talk about all those things and relate it to the electronegativity. You'd need to mention the shape of this molecule, which is trigonal pyramid, and that means that the polarities don't cancel, which is why we end up with a polar molecule anyway. And that's the first part of that question.